Hey there, it's Mrs. Painter. So just wanted to talk to you guys about how to understand magnetism and how it all works together. I apologize, I had not put the, what's it called? The PowerPoint onto RenWeb. It is there now, it's under Monday's work. If you go to the lesson plans, there should be a link for you to click on. So if you want to go through and watch those slides go through, it'll help you with your notes. Also, there's a video on there that I'd like you to watch. And in fact, if you wouldn't mind pausing this for a second and going and watching it. It's a little bit of a complicated video at first, but there's some good stuff in it that I think will be helpful. And then when we watch it, we're going to watch it again at the very end of the chapter, and hopefully it will all tie in. So I just wanted you guys to have that reference for you. So if you haven't gotten on PowerPoint yet and seen that, go ahead and pause this video for a second and go watch that, okay? If you have, I just want to talk about how things are magnetized in the first place. So magnets are produced, remember we said how magnetism and electricity are essentially two sides to the same coin. So that means whenever you have electricity, you essentially have magnetism, okay? And magnetism is produced by the motion of electrons. So that's that first blank for you there. Magnetic fields are produced by the motion of electrons. Now, electrons move in a couple different ways, right? They orbit around the atom, and actually as they're orbiting around the atom, they're actually spinning as well, okay? So think of the Earth, right? As the Earth rotates around the sun, it's moving because it's rotating around the sun, but we're also revolving as we go around, right? An electron is exactly the same way. As it goes around the atom, it's actually spinning on its axis as it goes. And it's not the revolution, but it's the spinning is what causes the magnetism. That's the strongest place where we get the magnetism from. So electron spin is the most important cause of magnetism in magnetic materials. Now, you've probably seen iron before, right? And sometimes iron is magnetic and sometimes it's not. And why is that? Okay? Well, that has to do with what we call domains. And domains are found within magnets. They're groups of atoms that are aligned the same way. So if you watched that video, you saw the iron lands and you saw how the land was divided up into these different stations, and you know, there were the red soldiers in the middle that were all standing upright, and on the side were the blue soldiers, and they were pointing downward, and they had all these different lands, and the soldiers were all pointing in different directions, okay? Each one of those lands with the different colors, that's the domain, okay? It's an area, a group of atoms that are aligned the same way. Now, if they're all facing different directions, that makes it not magnetic. In order for something to be magnetic, all of the domains need to be lined up in the exact same way. So the domain theory tells us that a magnet is the sum of the fields of thousands of magnetic domains. In other words, when all those magnetic domains line up, that's when we have something be magnetized. Now, there's a couple of ways that things can be magnetized, okay? And actually, if you look at the picture on page 332, it'll show you more of those domains and how the electrons in the magnetized steel are all pointing the same direction, and in the unmagnetized steel they're all jumbled up and the arrows are all going all over the place. So check out that picture too, okay? So substances can also vary in the amounts of magnetism they have, and that has to, so there's three different types of magnets that we talk about. There is the diamagnetic, the paramagnetic, and the ferromagnetic, okay? Diamagnetic simply means that that's substances that have no unpaired electrons. And in fact, they're not attracted to a magnet at all. They're actually repelled. They have a slight repulsion, okay? Let's see. There are a couple, so examples of this would be like copper, mercury, gold, table salt. They have no unpaired electrons. Now, there are some substances like aluminum and oxygen that are what we call paramagnetic, and paramagnetic simply means that they have one unpaired electron per atom. So you know how electrons spin around? There's always two electrons together, okay? or there's not always, but we like them in twos going around, okay? Now, if everything is filled up, okay, that means, so like you have a complete outer shell, or, you know, there's even numbers, so 2, 4, 6, 8, okay? Those are going to be, sorry, not 4. I said that wrong. Anyways, those are going to have no unpaired electrons, and therefore they're going to be diamagnetic. So all the noble gases, right? They have their electron shell is completely filled up. They are going to be diamagnetic, okay? Paramagnetic means they have one unpaired electron, okay? And like I said, aluminum and oxygen are examples of this, okay? They're going to be really weakly attracted to a magnet. You're not going to even realize they're magnetic, okay? And then the third one is ferromagnetic. Now it gets its name from ferrium, and ferrium is iron on the periodic table, okay? And so obviously that means iron is most of the time ferromagnetic, okay? It has several unpaired electrons per atom, and it's therefore highly attracted to a magnet. Cobalt, nickel are also ferromagnetic. So if you look at, when you're reading, it talked about the different types of examples here, and it gives you some examples of each, okay? Now, some things can be quickly magnetized, and we call those things magnetically soft, okay? Temporary magnets quickly lose most of their magnetism when the magnetic field is first removed, okay? Whereas a magnetically hard substance strongly resists changes in the directions of the magnetic field, and as a result they have permanent magnets, and permanent magnets retain their magnetism for long periods of time. So those are those blanks there. I encourage you to keep reading page 333 for a little bit more understanding about that. But I wanted to end with just a little bit about how you can magnetize or demagnetize something. So just like with electricity, remember there was 2 ways you could impart a charge. There's also 2 ways, well actually 3 ways that you can magnetize something, and 2 of them are the same as with the electrical charge. So we know the first one is conduction. Okay, so conduction means direct contact. So when we, in order to do this, objects can be magnetized by stroking with a magnet. Okay, this makes them permanently magnetized. So I have here, if I can find where I put it, I have here a needle, okay? And I also have here some staples. I don't know if you can see them, okay? Staples, they're there in my hand, okay? When I put my needle up to my, you can't see it, but when I take my needle and I put it up to this staple, it like, hold on, I already magnetized it, let's see. Ah, hold on, let me get a new one. I gotta start fresh. Yeah. Where'd they go? I'm so disorganized. I just found them. Yay. Hold on. So when I take my not magnetized needle and I touch it to my things here, nothing's happening, okay? They're not getting picked up, okay? But if I take this and I touch it to a magnet by direct contact, so it says you can magnetize something by stroking it with a magnet, I am now making this a permanent magnet, okay? So I'm going to just stroke it a couple of times. There you go. And then when I get to my staples this time, I can pick them up. I don't know if you can see that. There you go. So there I've picked up my staple and made a permanent magnet out of my needle, which is why when I did it earlier, I forgot that it was permanent. And so it's weakly charged now because some of it's gone, but it's still picking it up, as you can see. Okay? The other way you can do it is by induction, just like with electricity. And with induction, you place the object near and it will give it a temporary charge. Okay, just like with electrical charges, it is temporary, it's not permanent. The third way you can do it is with electricity, and you've probably heard of this before, an electromagnet, okay? An electromagnet is a device that produces a strong magnetic field when electricity passes through it. So, in other words, I can take a piece of metal, here, if I took some of this copper here, and I wrap it around an iron core, okay? And I wrap it, okay? It can keep wrapping and keep wrapping and keep wrapping. Then I take it and I attach it to a battery. Then this nail that doesn't pick up anything, right? It's not picking up this stuff here on my thing. Once I pass electricity through it, now all of a sudden this nail becomes magnetized and it starts picking things up, okay? And so I will show that to you at the end, provided my video doesn't cut out on me, but I want to get through the lesson, and if it doesn't cut out, then I'll show it to you at the end, okay? The strength of your electromagnet is going to be directly related to the square of the current, okay? And it's also proportional to the number of loops. So the more loops I keep adding to this, see, I'm wrapping the wire around it, the more coils I give it, the stronger it will be, okay? Now you can also demagnetize things. And so demagnetization is the losing of magnetism. And there's a couple ways you can do it. You can take a hammer and just strike the magnet over and over and over again. When you do that, you cause all of those domains that were all aligned, all those soldiers standing up in the same direction, they're now facing all different directions, and so it loses its magnetism. You can also heat it up. If you heat magnetisms, that causes the domains to get all messed up. The other thing, these are some bar magnets that were passed on to me when I came back to Calvary. And these are very, very weak. And the reason they are very, very weak is because they were improperly stored. And so they've been just sitting in a bucket all together, all jumbled up, okay? And as a result, the different currents from the different domains caused the domains to switch around and move, and they're just really not strong magnets anymore, okay? And so that improper storage, you actually want to, if you have two magnets, I meant to bring two home, but if you have two of these magnets, you want the other one to be the reverse if they're near each other. So you want the blue to be on top and the red to be on bottom, okay? And finally, the Curie point for Madame Curie is the temperature at which ferromagnetic domains disappear, okay? So in other words, if you heat something up to 773 degrees Celsius, pretty hot, and you, when you do that, the domains will disappear and it will lose its magnetism, okay? So let me see real quick. Brought home a battery here, hold on. I'm gonna attach this. Get my scissors. Sorry, I forgot to have this prepped beforehand, I meant to. And I forgot. So there's that. I took one end, right? And when I put it up to these staples, look, nothing's, oh, hold on, it's because I'm touching it. Okay, when I do that, nothing, oh, it is, they're all magnetized. What? Hold on. Don't you love it when your experiments don't work the way they're supposed to? Okay, hold on. And undo this for a sec. Okay, no electricity going through it. It shouldn't pick it up, but it is because these must have some magnetic charge left over from the last experiment. Hold on one sec. Need my stapler, which is behind me. Hold on. Give me one sec. I'm back. Sorry guys, I know this is long. You take it, and it should not pick up magnets, and I don't know why. There you go. It's not picking anything up, okay? Oops, there you go. Now you can see. So now when I attach it to my current, so I'm going to add it to my current from my battery here to what I'm doing, okay? Now when I do it, I should be able to pick up some of these magnets, some of these pieces. Okay, and I don't know if you can see that there is a staple hanging from my thing. Okay, so the more electricity I put through this, the more it'll go. And if I leave this on, you'll even feel it heat up because the electricity is coursing through it. Okay, this was a long one, I'm sorry. We'll see you tomorrow when we Zoom and answer any questions. And hopefully that was helpful. Love you guys. Miss you. Bye.